You have to
accept there. Okay. So, welcome everyone. In this talk, this talk is made to celebrate the 10th anniversary of the discovery, or better, the announcement of the discovery of the Higgs boson at the LHC. So if you go online and you look for historical events on the 4th of July, 2012, you'll for sure find that the scientists at CERN announced the discovery of a particle that has seemingly the same characteristics of the long sought after Higgs boson. Quite curiously, this is not the only thing that you will find. You will also find, You also find the recovery of a stolen manuscript from the garage of an employee of the Cathedral of Santiago de Compostela. I don't think the two events are connected, but I still find it amusing when I Google this. So anyway, I'm sorry for everyone interested in medieval literature, but I'm going to talk about the Higgs boson here. So let me start painting a description of what is the role of the Higgs boson in the standard model. So just to remind you where the standard model, the Higgs boson fits in the standard model. So the standard model is the theory that describes the interaction between the fundamental particles. These particles are fermions, leptons, and quarks that constitute all the visible matter, like electrons, up and down quarks, etc., etc. These particles interact with each other through exchange of vector bosons. Famously, the photon, that is the carrier of the electromagnetic force, the gluon, that is carries a strong force that keeps together the nuclei, and the W and Z boson that carries the weak force and they're responsible, between other things, for the decay of elementary particles. Now, it's important here to make a distinction between these two vector bosons and these other two, because these here are massless, while these are massive. In all of this, the reason why these are massive is connected to the existence, well, of the Higgs boson that fits here in this. Okay. So what is the role of the Higgs boson? Well, most simply, the role of the Higgs bosons is to break, or I prefer to say hide, one of this internal symmetry of the standard model. To visualize this, you can start from the fact that the potential of the Higgs boson has a shape like this. So this is a pictorial representation of the potential. And this potential enjoys a symmetry. However, the origin of this potential is not a minimum, rather is a local maximum. So when the Higgs rolls down from the maximum to the minimum, it chooses a direction to do this. And in doing this, in making this choice, if you want, it breaks the symmetry of this potential. This is a cascade effect on the rest of the theory. And the most important result of this sliding is that while you start with a theory with all massless gauge bosons, you end up with three massive gauge bosons, W plus and minus and Z, while the photon stays neutral. stays massless, sorry. So in this, with the same mechanism, the Higgs itself gets its own mass. What about fermions? So the Higgs interacts with fermions with the Yukawa coupling that is represented pictorially here. And with the same sliding, with the same breaking, the Higgs gives a mass to the fermions, and this mass is proportional to this Yukawa coupling. Now, this is, if you want, this is a side effect of the Higgs mechanism. Is not the primary its primary role in the standard model, but it's a nice side effect since we know that masses are there. Okay, so all this nice picture I gave you describes basically everything more or less from here to here. So these are in logarithmic scale. These are product mass and electroweak scale. So we have more or less a clear understanding of how nature works up to this point. However, we are missing many other order of magnitudes of unknown physics before we reach the point where we know that that quantistic effect becomes important for gravity. That is the Planck scale. Now, what was here? Well, we have no idea. There could be a desert and there could be only the standard model up to here, or there may be some new physics. So part of the role of the LHC is to actually try to gain some information. We know already though that the standard model does not represent the whole physics, and there are we need some new physics to explain some experimental evidence, like most precisely the masses of the neutrinos that are not completely well explained. Well, the standard model doesn't have a nice explanation for them. Dark matter and the Barren-Tavarian asymmetry or if you want, why we see only matter in the universe and where all the antimatter go. So how is this connected with the Higgs boson? Well, the idea is that if you study the Higgs boson and if you find some deviation from the prediction of the standard model for this particle, you can find this would be a sign of some BSM physics. And it could give you an answer to some of these questions here, or maybe it could help you fill up this gap, or at least have some intuition of what's here in this let's say deep hole that we have no idea what's there, or even like maybe connecting the two. So maybe there's an answer for dark matter here somewhere, and it could tell us where. So why this is of course true in general. It's not just valid for the Higgs boson, but for any standard model particle. Why the Higgs boson itself? Well, because it has a lot of different couplings with a lot of different particles. It has a lot of interesting physics going on, and it is particularly sensitive to possible new physics. It is incredibly easy to write a model of new physics that change the Higgs boson. So you can see that, well, this is the rationale why studying the Higgs boson is a particularly good place for understanding some of this. So to help you, to help guide you through this talk, I prepared this little roadmap. So we have the Higgs boson at CERN, and what we want to know if this object is a BSM object or the standard model Higgs boson. And we can go in two ways doing this. We can either hypothesize that it is a standard model Higgs boson, and then we try to falsify the hypothesis. So try to find ways where this hypothesis is inconsistent with other observations, sorry. Or we can try to use a general Higgs, BSM Higgs, and try to confirm that is this actually the object that we have. But first, it's worth doing a little trip to the past. So let's step in a time machine and welcome to the magic land of 2009. Well, that is the year of when run one of LHC started. So now we are before the run one of LHC. So what's the picture at that point? Well, the picture is very similar. We have, of course, from a theoretical point of view, the standard model is complete. We know the Higgs mechanism. From an experimental point of view, we know that there are all these particles apart from the Higgs itself. So we have pretty much everything. Now, the interesting thing is that at this point, even if we didn't have the Higgs boson, we knew that something has to be there. We knew that something has to be found at the LHC. And the reason for this brings back to what I was telling you before of a fundamental difference between the four gauge bosons, and that the W and Z have masses, and actually they really shouldn't. Well, they have, so what does it mean really shouldn't? Well, if you go and try to calculate the probability of the scattering of two W's into W's, so it's very easy to imagine. It is just the two W's that scatter to each other and go in other two W's. You soon realize that when you do this calculation, the probability for this process grows with the energy at which the process is happening. And this is a problem because it means that eventually it will be larger than one, and so it will break unitarity. And that cannot be possible since, well, we know that probabilities cannot be larger than one. And we know that this break happens more or less around 1 TeV. So we need something to help us correct this behavior before the 1 TeV scale. The Higgs is one of these possibilities. If you add the Higgs to the spectrum and you redo the calculation, this actually cancels exactly this anomalous behavior, and it gives you something that behaves correctly with the unitarity. So quantum field theory is, well, I mean, the massive gauge bosons are not consistent with the quantum field theory if you don't have some mechanism to give them masses, some external object. Okay, now the interesting thing though is that the standard model is just one of the solutions. It's not the only one. I'm not going over the other possible solutions. We are not here to talk about them. But at least to point out there are other possibilities. And I could argue that at least in 2009, the standard model Higgs was not, in fact, the preferred solution for this puzzle. And well, you say, well, it's weird because everyone studies the Higgs mechanism. It's true. But there are a few striking things that that make you think that maybe something fishy is going on. And these three are the fact that the standard model Higgs is a scalar, the fact that there are tensions between different experiments, electroweak precision experiments and direct searches experiments, and there are tension between electroweak precision observables and the theory. Let me go over this three quickly. So first, the problem with the standard model being the standard model Higgs being a scale. So in nature, we do not have other elementary scalars apart from the Higgs. We have pions, but those are composite objects, so they don't count. So the Higgs already starts being a weird thing. It's the only scalar in particle physics, a high energy. But this is not the only problem. The problem is that scalars are actually more susceptible to quantum effects that derive from BSM, more than gauge bosons or fermions. That means that you can make some argument that the natural value for the mass of the Higgs should be somewhat around the cutoff of your theory that eventually is the scale at which gravity becomes quantisical. So that means Planck scales or 10 to the 15. But we know already that for the unitarity, the Higgs most natural mass should be somewhat below the 1 TeV. So there is evidently a strain here because we have 10, 15 order of magnitudes of difference. So these things tells us that the mass of the Higgs appears to be unnatural, according to this reason. So this is point one. Point two is some tension between electroweak precision observable and experiments. So the standard model predicts a simple correlation between parameters. We saw that already, for example, for the proportionality between the Yukawa coupling, so the coupling of the Higgs to fermions, and the mass of the fermions, that in the standard model appears to be, it's something very easy. However, this is not the reality, because reality has, is the fact that dark field theory is a quantum field theory. So there are quantum corrections, and this quantum correction spoil the simple relation that we had before. Well, there's still proportionality, so that's already something. However, it's not as easy as before. So this is a problem when you try to check your theory against the experiment, because you have to take into account all the quantum corrections at the precision at which your experiment is measuring these. However, we can also, so this can be also used because we use in our favor, because all the corrections includes anything. So everything in the theory contributes, even things that you have not seen before. So for example, the Higgs boson in 2009. So let's go on a more concrete example. So we have here a relation that you can write between the mass of the W and other observables. These observables are, well, the mass of the W and the mass of the Higgs boson. The Fermi constant that is related to the lifetime of the muon, and the fine structure constant that everyone knows very well. Now, quite interestingly, all of these objects are very, very, very well precisely measured. Actually, these are the most well measured observables in particle physics, in high energy particle physics. So this relation is true, of course, at any order, because we added here this little function delta R that contains all the contribution to quantum correction. So when you put delta R to 0, this is simply the tree-level relation, and all the quantum contribution, all the perturbative contribution to this expansion comes in this delta R. Now, delta R includes logarithmic contribution proportional to the mass of the Higgs. So since we can measure very well all of those observables before, we can use it to predict the mass of the Higgs. And that was done, and this is a paper from 2009, so we are still in our time. And this paper predicted from those measurements a mass of the Higgs of around 80 GeV. Here we have, so in this graph, we have the mass of the Higgs against the probability and the chi-square, and you can see that the minimum is here around 80. The green bands are the exclusion bands from direct experiments at lab. And you can see that these exclude the mass of the Higgs that the electron position observables predicts by more or less 1 sigma at least. So there is a tension here. Of course, it's not a huge tension, it's 1 sigma, but still is large enough. Well, it's something that makes you think that maybe there's something something more going here. Now, there is another tension I was talking about between those electroweak precision observables we saw before and the vacuum stability. So let's go back to our friend, the Higgs potential, that now we write in a more, in explicit form. So when the Higgs slides down, the Higgs potential acquires this shape. This is true, however, around the origin. So this is true around this middle, around the origin of this potential. So the one can ask the natural question of what happens, this potential, when you go very far away. And so there are 3 possibilities. One is that it grows forever, or maybe it goes down a little bit, but then grows forever. And that would mean that the minimum where we are, the electroweak minimum that we calculated and where we enjoy living, is stable and will be stable forever, and everyone is happy. Second is that actually it goes down at one point, and that would mean that this potential is unstable. And unstable potential means that, well, we cannot be here. So this potential would tell us that we cannot exist because, well, there wouldn't be any electroweak vacuum. The third possibility is that the potential itself is stable, but the minimum is not. The minimum where we are is not, and it would actually eventually transition to some new state, new minimum that is a deeper, and well, in this case, until we are here, we are enjoying our life. But as soon as we transition here, and everything will stop existing. No chemistry, no biology, not even just physics, actually. So that would be an interesting. Let me make my study easier. Anyway, so as you can see, the physics is very different in all 3 possibilities. So it's worth investigating, or at least it's useful as to put the bounds. So in 2009, again, the same paper gave us the bounds. And if you, okay, here we have the mass of the Higgs against the scale at which you think the standard model should be valid. So this here means that the standard model is valid up to the Planck scale. So there is nothing else, no other theory up to the Planck scale. And in this case, if you consider that, the complete stability requires a mass of the Higgs of around 130, more than 130. This can be relaxed a little bit if you move down just a little bit. Now, interestingly enough, 125 seems unstable here. Just so. Anyway, but this is a problem for the electroweak precision observables, because again, the electroweak precision observables tells us the mass of the Higgs should be around 80 J. So there is evidently a tension between the theory, the theoretical prediction of the mass of the Higgs, and the theoretical prediction of the existence of our universe. So, so all of these 3 together, they don't tell us that the standard model Higgs is excluded, but they tell us that maybe it's not a fair answer. And this is why in 2009, many scientists believed that there wasn't any way that we would find the standard model Higgs, the standard model Higgs at LHC. I remember a professor that told me exactly this word. But of course, we find it. So again, on the 4th of July, we found something that looks like a standard model Higgs. So now the question becomes, is this really the standard model Higgs? So is this really the Higgs that is predicted in the standard model? How can we know? Okay, this thing starts. Well, we have, let's say, 3 things that we can check, and if any one of these show any deviation from the standard model, then that would be a signal of new physics. Quantum numbers, the couplings to other particles, and the couplings to itself, so the Higgs potential. So the quantum numbers, well, first of all, we exclude pretty much spin 1 because there is a theorem that says that if a particle decays into photon, it cannot have spin 1. So that's already something. Now, the experimental is mostly concentrated on the hypothesis that this object is spin 0 with plus or minus. Yeah, I'm sorry you don't really see it. Here is a plus and here's a minus sign for the parity. These are different hypotheses for a spin 2 particle, because of course it could be a spin 2 particle. And there have been many studies, but already in 2015, sorry, here is the probability. This is the probability that is a standard model with respect to the probability of not being a standard model object. And you can see that in all cases, the winning hypothesis is that it is indeed a spin 0 parity plus object. So something that is a scalar. So the 125 GeV particle is quite surely a scalar as predicted for the standard model. The next step is the coupling, is the measurement of the coupling of the Higgs. And we know that the coupling of the Higgs to particles are proportional to the mass of these particles. So these are, well, nearly the most recent result. By the way, so the most recent result, many of these results are at least 1 or 2 years old. And the reason is others and CMS didn't really give us a lot of new data, and the reason is that they're probably giving everything on the 4th of July of this year. They have a big party at CERN, and they will have all the plots. So probably all the plots I'm showing here will be outdated in a couple of weeks, but well, this is what it is, and you're invited to actually go look at the new plots in a few weeks. But for now, this is what we have. So these are the results for the coupling, different couplings with respect to the mass of the particles for mu1, the 3rd generation fermion, and WZ. And you can see that, well, they are perfectly on this line that represent the standard model Higgs boson. So for now, we saw that they're very close to the prediction of the standard model. However, there's still some largish uncertainty, in particular for the mu1 here, for the bottom. This seems pretty good, but I mean, there's still some room. So one could argue there are 2 directions to improve this plot, and one is to increase the precision, and to try to measure the missing couplings. That for now means the other 2 2nd generation fermions. So for 1st generation fermions, I don't think there is anything we will see for many years. But for now, let's so for now we can concentrate on 2nd generation. So when we go for precision, it's useful to define a kappa framework. So a kappa framework is simply the idea that you start with the standard model Higgs, and then you modify all its coupling to the other particles through some kappas. And then you try, so any variation from kappa equals 1 is somewhat related to the scale of new physics. So if you can measure this kappa very well, or if you can bound it very well, you can get information of where and maybe what kind of new physics could appear. So the most precise you can be here, the higher scale you can start. So again, the nearly most recent results from Atlas on this are this one here. So here we have different kappas. For example, we have a kappa to the Z, a kappa for the W, but we also have a modified coupling to gluons and photons. Now you'll tell me that the Higgs doesn't couples directly to photons. However, it couples through loops. So this is a rescaling of the loop interaction. These two plots differ from here. The hypothesis is that everything the Higgs decays only in standard model particles, while here this is relaxed, and you can consider also decays into dark matter, for example, or other invisible object. And well, these are the results for now. So we have, in general, they're pretty nice, at least these ones. We have precision of about 10%, I would say, 10, 15% of all of that. So this is our present understanding. And this is more or less compatible with some new physics that appears around 1 TeV or more. So for now, we cannot exclude from here physics that are higher scale than 1 TeV. Of course, what we really would like to see is something that is completely off from this one, but well, we are not so lucky, or nature is not so generous with us. For the measurement of other couplings, for now, the next challenge is the measurement of the coupling to the charm. So here we have some recent bounds that come from different processes here. In this plot, we have the coupling to the charm, kappa charm, actually, the variation of the coupling to the charm against kappa B, the version to the bottom. And now, the most interesting thing here is the fact that we have no idea what this kappa C is, because you can see that we are very far from being 1. The limits are 10 or 20. So we are very, very far away from here. But maybe it's possible at high luminosity LHC. Okay, so let's go to the third things, and that's the measurement of the Higgs potential. So again, let's go back to our friends. And we know this Higgs potential, it's from the theoretical point of view, it's perfectly known, because once we measure the mass of the Higgs, all the other coupling, all these terms here in front of the potential are known, since, well, we know that B is connected to the Fermi constant here. So from an experimental point of view, what we need is to make a determination of the extra linear stealth coupling, meaning this term here, the term in front of the Higgs cube. This process is, this measurement is particularly difficult because it's a measurement that involves in order the production of 2 Higgses. And that makes the probability for this cross-section, so the size of this cross-section, extremely small. So imagine you produce 1 Higgs of shell, and then the Higgs decays in 2 Higgses on shell. So this is a very difficult object to observe. Now there is another channel that another possible channels, and these are channels that involve a single Higgs. So for example, a single Higgs that decays into vector bosons, the trilinear enters in loop correction. So you have to go to a loop correction. So while these are much better measured than these here, you have to deal with the added problem of dealing with loops. As before, all the results are given in terms of the kappa lambda, that is simply the variation of this lambda state as a standard model. So the best limit in this moment are these, for the kappa lambda between -3 and 8. So again, we want something around 1 possibly. So we are very far from it. And they come from here, from the cross-section of the production of Higgs that goes into photon, and BB bar. And these are the results. And well, this is the limits. On these other plots here on the right, instead we have some preliminary results from Atlas for searches in double Higgs, single Higgs, the blue line. So the black line is double Higgs, the blue line is single Higgs, and the red line is a combination of the two. And this shows you that more or less when you singularly, they're not particularly good, but when you combine the results of double Higgs and single Higgs, you actually get some more stringent bonds. Now, all of these have some problem because actually you always require all the other couplings to be one. So this is, of course, this means that you are studying a particular BSM, but particular new physics where all the other kappas are one and only the trilinear is different. So we go back to our roadmap, and now we have, so this BSM Higgs, let's say that it's mostly compatible with standard model Higgs. For now, we really don't have anything that tells us that it's not. But we have a lot of studies to do because, again, we don't have all the couplings, we don't have the self-couplings at all. So there is still room. For now, it's compatible, there's still room. So what about these three? Now that we actually have the standard model Higgs, let's see what happens there. So first is the stability of electroweak vacuum. So in this plot, we have the mass of the Higgs and the mass of the top. Here we are assuming that the standard model Higgs is the only theory up to the Planck scale. So the green region is the pure stability, the red region is the pure instability, and the yellow is the metastability. Well, this region here simply means that it's a region where the standard model becomes non-perturbative, so we cannot really make a projection here. But in any case, we are here in this little circle. So if we zoom in, we obtain this picture. Again, we have the mass of the Higgs against the mass of the top. And again, we have the region of stability, metastability, and instability. And we are here in the center of this oval. These oval are the 1, 2, and 3 sigmas uncertainties on the mass of the Higgs and the mass of the top. And by the way, these are actually new results. So these are obtained with a new PDG 2021. So again, even now we are like 3 sigmas away from pure stability. So for now, the preferred scenario is a metastable vacuum. What does it mean? Is that a bad thing? Well, not really, because the decay of time here, it's something around 10 to the 200 years. So we cannot really distinguish between this and a completely stable vacuum. So this is perfectly compatible with our understanding of the universe. Now, quite interestingly, there's a new measurement from CMS, quite recent, that pushes this mass of the top down by nearly 1 GeV. And that brings it very close to the line that divides the metastable and the stable vacuum. That actually is a pretty interesting, because that's actually a pretty interesting thing, physically speaking. So maybe if this trend continues, that would actually maybe tell us something new. That would be interesting to see. But for now, we are here. Now, for the tension between the electroweak regional observables and the measurement of the mass of the Higgs, those now, these days, translate to a tension between the electroweak regional observables and the measurement of the W mass. So before April 2022, these were our results for. So this blue blob here was the measurement, was the theoretical prediction of the mass of the W that is obtained as we with the same formula I showed you before. While these green here are yellow, but they're green bands are the measurements. And at the time, the inconsistency was around the 2 sigmas. Well, this is not surprising because we saw it was 2 sigmas at the time of 2009, so it's still just a 2 sigmas tension rather than inconsistency. Now, recently, the CDF gave us a new study of their measurement of the mass of the W, and that now implies a 7 sigma tension, partly because their center, the center of the hole is pushed here, and partly because and most importantly, because the uncertainty that they quote is extremely small. Now, I have to say that the result is a little controversial in this moment, since it looks like it goes against all the other measurements that we have done about the mass of the W, and the uncertainties that they quote seems a little optimistical. So I'm not really sure. But if it is true, if it is confirmed, then that would be a proof that new physics is at LHC. So there is new physics behind the corner somewhere. So last one was naturalness. So the naturalness tells us that new physics should appear around 1 TeV, but nothing has been found until now. You can push it a little further from 1 TeV, but the more you push, the less consistent this requirement becomes. So at this point, my only thing is naturalness actually a good principle to look for new physics? I don't know, and I leave it at that. So this is the end of the way for us. For the present, today, these are understanding of the Higgs boson. We don't know if it's a standard model Higgs boson. Something tells us that the thing that for now everything is compatible, but there is room to find new things. So it's not a closed road here. Same thing for the BSM. Everything looks standard model. Everything that we measured looks standard model, but there's still a lot of things that we haven't measured. So I'd like to conclude talking about the future. So I talked about the past and the present. So where are we going? Well, the community has a lot of interesting thought of a lot of possible new machines that can test the standard model, and in particular the LHC, the Higgs. The high luminosity LHC here is the only one that I think is probably confirmed 100%. And this year. The other ones, I'm not really sure what is the situation right now, but these are different roads, as you see, different possibility. And some of them talk about running up to 2090. So I don't know. I think everyone here will be either dead or retired at the time. So I don't know if this is actually very optimistic or not. But in any case, there is a lot of things that people are thinking. So let's hope. What are these telling us about the Higgs boson? Well, already for the high luminosity LHC, so the one that we know that is going to run in about 10 years, we already are going to nail down these kappas. So these are, you cannot see here, but so these are kappas, the different kappas, and these are, well, you can see here, these are the estimated uncertainties. And you can see that we are talking about 1%, 2%, where now we're talking about 10, 15%. So we are really pushing further on how well we can do on this. Unfortunately, though, for the kappa lambda, so the Higgs potential, things looks a little bit bleak, more bleak. Still, I mean, high luminosity can tell us something about 50%. That is much better than the 800% that we have now. But in order to look for precision, we really need to look for the FCC. Now, I need to say that these results are actually, this prediction, well, prospect, let's say, not prediction, are actually a couple of years old. And the new one that will come out, I think, very soon from this no mass report, show actually that quite a big improve here. Some of these are slicing out. So FCC goes to 2%, for example. So There is this prospect is actually improving. So this at least is well, somewhat nice. So this is where we are now. So the discovery of the Higgs opened the possibility to challenge the standard model, our understanding of the nature, and this measurement of the covering of the Higgs boson can tell us something on the physics. But of course, we are talking about a very challenging new physics that appears. And I talked here mostly about experiments, but of course, from the theoretical point of view, also all the predictions becomes extremely challenging the more you want to go into precision. So there is a lot of work here to be done for all groups, theoretical and experimental. But there is a lot of exciting physics that hopefully is coming our way from LHC and the accelerator. So with this hopeful image, I conclude my talk, and thank you very much for